Welcome back for ME 760 Engineering Analysis 1. So I have a comment regarding the exam. The exam will be 6 problems. One problem from chapter 9. It will be regarding vectors. So if you know the scalar product and dot products, you will be able to solve this problem. There is 3 problems from chapter number 10, which is matrices and linear vector spaces. 2 of them are just normal matrix work, and the third one is from the spectral radius sort of type of work that we did here in the class. If you will concentrate on the couple of lectures for the spectral radius, you will be able to solve it in no time. No time. Just understand the material, you will solve it in no time. And then there is 2 more problems from vector calculus, and they usually stuff like divergence and curl and all those types of work. So it's again very easy problem. So six in total. Hopefully, if you are prepared, what do you mean by prepared is, what do I mean by prepared is you knew what are you doing. Not prepared that you will come to the class with 17 books and several hundred of cheat sheets and stuff like this. No. You understand what you are doing. It will not take 15 minutes, the exam. I promise. If you are prepared and you understand the material, it should not take more than 15, 20, 30 minutes at maximum. You have an hour. So hopefully this will help everybody. So I hope that you will understand this first. So everyone got my PDF file that I sent to everybody a couple of days ago regarding the cheat sheets. This is very nice cheat sheets I got from the internet for the reactor physics class that I am teaching, and I took the permission from the professors who published this online, and I sent it to you. I put everything in one PDF file, and I give it to you. So this is very handy. Whenever you are in an exam, for example, and you need a formula, just look at this one. It will be very handy in the class. Just do diligence and look at those cheat sheets. Print them and look at those cheat sheets a day or 2 before the exam, so that you will know beforehand where to search. Because if you bring this to the exam and this is the first time for you, then you will start, oh my God, oh my God, oh my God. Then you will lose consciousness, and it will be very, very bad for you. So I urge everybody to print it out, look at the cheat sheets, bring them to here. In this case, it will be very easy. If you want to look something up, it's here. You knew where it is. So you can put even a table and say, okay, calculus will be page number 1, number them, page number 1, trigonometry page 15. So at least you knew where to search. So this is the best way. So let's finish chapter number 11 and get into chapter number 12. So last time we said that the divergence of a curl of a vector is equal to 0, and this is just all what you will do. You will say the divergence of a curl of a vector v is nothing more than I jk, and this is the divergence with the curl, and curl is what? D by dx, d by dy, d by dz. Again, this is vx, vy, and vz. So this is the divergence with the components here will be what? D by dx, d by dy for vz minus d by dz for vy in the I direction. So let's make it like this. Minus in the x direction, it will be d by dx for vz minus d by dz for vx, and this will be in the j direction. And you will have the third one will be d by dx for vy minus d by dy for Vx. But in this case, you have to remove the divergence here and put the three components, which is d by dx in the I plus d by dy in j plus d by dz in k. And then you will run I by I will give you d by dx multiplied by this one. I dot j is 0, I dot k is 0. So it will be d by dx for this and d by dy for this and d by dz for this one. So let's do it. So this will be d by dx dy for vz minus d by dx d by dz for vy plus minus d by dy d by dy d by dx for vz minus minus is plus d by dy d by dz multiplied by vx, and then plus d by dz d by dx for vy minus d by dz d by dy for vx. So what is dx by dy? This is 1 dx by dy vz, and this is dx by dy vz. So 1 cancel with 1, and this is, we call it 2 dx by dz. What is dx by dz? Here it is for vy. So this is 2. So 2 will cancel with 2. Then where is d by dz and d by dy? Here it is. So this is number 3, and this is by vx by vx. So this one will cancel with this one, and the results will give you 0. And this is the proof for this one. So divergence of a curl of a vector function equal to what? 0. So divergence, if you have divergence of v, a vector v equal to 0, I can then write v as what? Curl of another function, a vector function called a. Why? Because if I substitute with v here, equal to what? Curl of a, divergence of a curl of a equal to what? 0. So if you have a divergence of a vector function equal to 0, you can represent this vector function as a curl of another vector function. And this is what I talked to you last time about Maxwell equation, divergence of B equal to 0. What's B? Magnetic field. What does it mean, divergence equal to 0? Divergence theorem, the divergence theorem, do you know the divergence theorem? It states that if you have divergence of a function f, you integrate this over a volume, this will give you the same function f integrated over the surface area. This is the divergence theorem. We will take it in chapter number 12 in the line, surface, and volume integral. This is called Green theorem. Green theorem. Okay, it's called Green. Sometimes they call it divergence. Sometimes they call it Green theorem or divergence. Green or divergence theorem. If you have a divergence of a function f over the volume, so you integrate the divergence over the volume equal to the surface integral. So if the divergence of the function is equal to 0, so what does it mean? It means that your function, the integral of your function over the surface is equal to what? Is equal to 0. A certain vector function you integrated over a surface is equal to 0. So if we apply this over electrostatic told me that the divergence of the electric field over the volume is equal to what? The electric field dotted at the surface. Yes? But Gauss' law told me that the electric field, the integration of the electric field on the surface is just equal to the charge, total charge inside the volume, divided by what? Divided by epsilon naught. Okay, guys? Which is the permittivity of the free space. So this is, what does it mean? Divergence of E dV is equal to the E dot ds, but E dot ds is equal to what? Q over epsilon naught. What this formula says is the volume, the divergence of the electric field inside the volume is coming from the charge. So the source of the electric field inside this volume is coming from what? The total charge inside this volume. And what this is telling me, it tells me that the electric field coming out from the volume is because of the existence of certain charge inside this volume. Okay? So this is Maxwell, this is the Gauss law for electrostatic. So if I have the divergence is equal to 0 like in magnetostatic, this means that I do not have a net the electric field, in this case magnetic field, I do not have a net magnetic field coming out from the surface. So, but why? Because in electrostatic, if you have a charge here, point to charge, the point to charge will have what? Will have electric field, if it is positive, coming out from the charge outside. But if you have, for magnetostatic, if you have a magnetic field, you cannot have north pole or south pole alone. Yes? If you cut the magnet to half, you still have north and south, and here is what? North and south. Yes? If you cut this to two half again, north and south. Cut it to two half, north and south. You will never be able to find a magnetic monopole. Theoretician, particle physicists and stuff like this, they said that it exists, but they never find it in nature, in experiment. But experimentally, you will never find a magnetic monopole that will have only north or south only. So what does it mean? This will emit what? Field lines in what direction? Out. Then it will do what? Rotate and come back. So if you look at the number of field lines getting outside the volume and the number of field lines that get inside the volume, and you do just E B dot ds. So this is just what? This is just the summation of all the magnetic field line that crosses the surface, the positive minus the negative. What gets out minus what gets in. So what gets out is exactly as what gets in. So the net is what? 0. So what this formula is telling me is there is no source of a magnetic field based on only one pole. So this is called no monopole theorem for the electrostatic. So in this case, I can, because this is divergence of B equal to 0, I can represent B as a curl of another vector. And this other vector here is called the magnetic, because it comes from magnetism, and it's a vector because A is a vector, is not potential, and it's called magnetic vector potential. So in electrostatic, if you have divergence E in electrostatic is equal to what? Rho over what? Epsilon naught. It does not equal to 0. Divergence E does not equal to 0. Okay? Because the electric field is coming from a charge. But the other equation, which is the Faraday equation, curl of the electric field is equal to negative dB by dt, this is the time rate of change of the magnetic field. If the magnetic field in electrostatic is 0, if d by dt is 0, so we have magnetostatic. Magnetostatic mean electrostatic, sorry. What does it mean electrostatic? There is no magnetic time rate of change of magnetic field. Maybe there is a magnetic field constant, but it does not change with time. So if it does not change with time, dB by dt is equal to 0. So curl of E equal to 0, we can, if you have curl of a vector equal to 0, you can represent this vector as a grad of a scalar function. So in this scalar function, I call it V. So this would be curl of a gradient of V. If you do this, if you do curl of a gradient, this is 0. Curl of a gradient of a scalar function is 0. So I can put E equal to grad V. Grad what? Grad V. And V in this case will be what? The electric scalar, because gradient of a scalar potential, which is what? What's the potential in electrostatic? What does it mean? Huh? Yeah, but what's the, when I ask you to measure something, the potential? Yeah, the voltage. So this is the voltage. Okay, guys? So this is why in electrostatic, I can write the electric field as gradient of a scalar potential. In magnetostatic, I can write the magnetic field as a curl of a vector potential. Okay, guys? Did you understand the difference? This is just in electrostatic, in electromagnetic theory. Okay? So I'm not going to stress more in this, but this is just to teach you something about the scalar potential and vector potential and electromagnetic if you encounter in your future research or something like this. So now there is some important formulas, and you will find it in your cheat sheet. And those important formulas are the gradient of a scalar function f and a scalar function g is exactly the same when you do the partition, differentiation by partition. So this would be what? The first multiplied by the differentiation of the first, the second plus the second multiplied by the differentiation of the first. If you have a division now instead of multiplication for two scalar functions, f over g, this will give you what? 1 over g squared, yes? Then the denominator multiplied by the differentiation of the numerator minus the numerator multiplied by the differentiation of the denominator. So it's exactly the same like the differentiation rules for multiplication or division of functions. Now, if you have the gradient of a scalar function multiplied by a vector now, and I told you that the gradient of a vector is what? So a gradient of a function, scalar function, it's okay, we knew it. It's a vector. A gradient of a vector. No. Gradient of a vector is a tensor. It's a 9-component dyad. It's called dyad, and it's third order dyad. So this is called, second order dyad, because 0th order is a scalar, first order is a vector, second order is a tensor. So this is a tensor. Okay. So now this would be what? This will be f. This will be f. Now multiplied by divergence of v, because v is a what? V is a vector, so I have to put divergence of v, plus v dotted with the gradient of f. So if you have divergence, this is by the way, this is divergence. So you have to put here a divergence. So if you have a gradient, it will give you a tensor, but this is a divergence. So if you will put a gradient of v, this is another story. This is tensor. So divergence of f multiplied by gradient of g. So this is exactly the same. So if you follow this, this will be what? F divergence of j, of gradient of j, plus the gradient of j dot the gradient of f. What's divergence of gradient? What's this? Huh? What's this? When you have two vectors dotted with each other, what does it mean? Square. So this is nabla square. Nabla square what? G plus grad G and grad F. Again, nabla square is just equal to the dot product of the two del operators. If you have nabla square of two functions, f and g, and instead of just gradient of f and g, so nabla square of f and g. So nabla square is what? Is it vector or scalar? Scalar, because it is divergence of what? Or del dot del. It's a scalar quantity. So I do not expect that I will have like here. This is the del of fg, and this is nabla square of fg. So I do not expect vectors. Those are what? Those are vectors. So here it will be what? It will be g nabla square f plus what? Plus 2 divergence of f, a gradient of f, sorry, and multiplied by gradient of g, plus f nabla square g. Do you remember it's like what? Like when you have binomial of what? So this is x square plus 2yx plus y square. Just remember it like this. Okay, guys? Remember it like this. So now the curl of f v is equal to gradient of f curl v. So you operate this over the first multiplied by the second, and then the differentiation of the second multiplied by the first. Okay, differentiation of the first is just, this is a scalar function. So you cannot say curl of f, because f is a scalar. There is no curl of a scalar function. So the only way is to do the differentiation of a scalar function is to say what? Gradient of what? Gradient of f, and this is what we did. Multiplied by the second, but this is a vector. And I have to keep the same multiplication, cross multiplication. So this will be crossed with what? With v. Do you expect what's the second one? So f multiplied by what? So it's the first multiplied by the differentiation of the second, plus the second multiplied by the differentiation of the first. But I have to keep in mind what type of multiplication. Is it dot or is it what? Curl. Is it dot or cross? And again, I have to keep in mind that this is what? Whether it is a scalar or a vector function. What about divergence of u cross v? U cross v. So this will give me, again, the first one is u dotted with the curl of v minus v dotted with curl of U, or make this U V, and this is U V. So this one is not like the normal way, the first multiplied by the differentiation of the second, plus the second multiplied by the differentiation of the first. There is a what? A negative sign here. Okay, guys? Now, the curl of grad f is equal to 0. And this is what I wrote to you here. If you have curl of E equal to 0, curl of E is equal to 0, I wrote E as what? I wrote E as what? So curl of E, I wrote E as gradient of V, and V is a constant, as a scalar. So this is exactly the same. Curl of a gradient of a scalar function is equal to 0. This is what you see over there. And divergence of curl of U is also equal to 0. This is equivalent to the case of what? Magnetic field. So divergence of a B equal to what? 0. I can represent B as what? Curl of A. So this is exactly the same. Divergence of curl is equal to 0. So if you want to remember it, just divergence of a curl is equal to 0, and a curl of a grad is equal to 0. Okay, guys? And finally, we have curl of a curl. So curl of a curl of V is equal to gradient of divergence of V minus nabla square V. And again, if you have something like gradient of F multiplied by gradient of G, this does not equal to 0. So this, not to make confusion with you guys, that it is equal to 0. Now, the rest of the chapter is talking about the curvilinear coordinates. So curvilinear coordinates mean generalized coordinates. So how many coordinates when you encounter in your study of mechanical engineering or any type of engineering? Usually what? The simplest one we use always is what? Cartesian, X, Y, and Z. And the second one is what? Cylindrical. And the third one? Spherical. And there is something called curvilinear coordinates. And usually it has a parameters H and U1, U2, U3, and so on. And if you want to decompose your vector instead of Cartesian or cylindrical or spherical, you can decompose your vector in any types of curvilinear coordinates. And curvilinear coordinates, they are not necessarily that they will have perpendicular vectors between them. Like I, J, K is perpendicular to each other. R, theta, and Z in cylindrical, they are perpendicular to each other, and R, theta, phi are perpendicular to each other in the three coordinates. So let's look just as a rough representation of the three coordinate systems. So we have a cube like this. The unit volume of this cube, if this is X and this is Y and this is Z, the unit vector will be what? Delta Y, delta X, and delta Z. So this would be what? The volume delta volume will be equal to delta x, delta y, delta z. So if you want to get the unit volume and unit area, it depends on what direction. So the unit area in the xy plane, for example, will be delta x, delta y. So this is delta area in the xy plane, delta area in the zy plane, which will be delta y multiplied by delta z. This is in the yz. So delta area in the yz will be just delta y, delta z, and delta area in the other plane, which is xz plane, will be just delta x, delta z. So again, you have the three unit vectors are I, j, k. In cylindrical and spherical geometry, in cylindrical geometry, let's look at this. So this will be the Cartesian, and in the Cartesian, usually you have the point is represented by what? By three different. So this is z, x, y. So the points here will have rho, which is r. I will give it an r here, and we'll get what? A z. Then we'll get what? Phi in this direction. So any points will be represented as r, phi, z. Any points here will be represented as let's say this point x, y, and z. Here it will be phi, r, and z. So any point will be represented by r, phi, and z. Now let's look at if I want to move from phi 1. If I want to move from phi 1 to phi 2. So you move from phi 1 to phi 2. Phi 1, you were here, and this will be the corresponding here. So you'll have same like this. So what's the arc length here? So this is delta theta, or delta phi, sorry. So this arc length is what? R delta phi. And what's the height here? So this is r delta phi, and this is, let's say, z or delta z. Let's call it delta z. From here to here, delta z. So the area of this thing is what? Is equal to r d phi dz. Okay, guys? Okay? And if I have delta r, so I go from r1 to r2, so this will be my delta r, and this will be the corresponding delta r. So in this case, this will have a delta r. So this is delta r. So the volume in the cylindrical geometry will be what? Will be delta A multiplied by delta R, and this will be what? R delta R d phi dz. Okay, guys? Did you understand how to get a unit volume? If you want to integrate, we will use this a lot in the volume integral or something like this in cylindrical geometry, if you want to use it. And in Cartesian, it's just the dx, dy, dz. Here is r, dr, d phi, dz. So let's look at the spherical geometry. So for spherical geometry, this is the coordinate system again with respect to x, y, and z. And before I leave, what's r? R is just equal to what? X. Or yeah, or let's say x. What's x? It's r cosine phi. And what's y? R sine what? Phi. And what's z? Z. So those are the relation between the Cartesian and the cylindrical geometry. Now, in a spherical geometry, I can represent the point here by three things. By r and by its projection here. So I'll have phi. So this is phi, this is theta. So the point can be described by a position which is r, and this is the azimuthal, and this is the angular. So theta is the azimuthal and phi is the angular angles. Okay, guys? So what's the relation now? What's x? X. So this is 90 degree. So you decompose this one here. So this is again theta. Yes, guys? So this is r cosine what? R cosine or r sine? This is r cosine. This is r sine. This is r sine theta. And this is r cosine theta. And then you decompose it in those two directions. Okay, guys? So this is 90 degree. So this will be r sine theta cosine phi here. R sine theta cosine phi. And in this direction will be what? R sine theta sine phi. Okay, guys? So x will be what? R sine theta cosine phi, and y is equal to what? R sine theta sine phi, and what's z? R cosine theta. So those are the relation. Now, if I want to do a volume, so what happens is this r, I will make it move between phi 1 and phi 2. So this will be delta phi. Okay, guys? So I will have 2 points. I'll have the first point here, second point here. So I'll have something like this. Then, I'm sorry that I'm just blotting in the same thing here. So we will have this one and this one. But now I can make this r go in the theta direction to here. So I will have also d theta change in this direction. And what this will make a unit area. A unit area in what? On the surface of a sphere. Then I can take, if the sphere is solid, I can take delta what? Delta r. So this will be just a spherical shell, like a sphere like this, and you take just this is a unit, an area on the surface of the sphere. Then you go inside, and you take something like a spherical shell or something like this. So the volume of the spherical shell, this will be what? What's this? This r here is called what? R sine what? So this will be r sine theta delta what? Delta phi. So this is r sine theta delta phi. And this in this location, what's this? It's r multiplied by what? Delta theta. So this location is what? R delta theta. And what direction? In this direction, in the r direction, this is what? Delta r. So the cross-sectional area here is just r d theta multiplied by r sine theta d phi. So delta A is just what? R square delta theta sine theta delta phi. And what's the volume now? Is delta r multiplied by delta A, and this equal to what? R square dr sine theta d theta d phi. Did you get it? Guys, did you get it? One hint here. If I asked you that this is the coordinate here, and now something like this. So there is some cone, something like a cone in 3D. I can better represent it like this. So this is R, and this area is what? R square sine theta d theta d phi. Yes, guys? Yes? So if you want to rotate delta phi all the way around, this will give you what? 4 pi. Phi goes from 2 pi. 2 pi. And theta goes from 0 to 90 degree, to pi. Okay? 180. So this one phi goes from 0 to 2 pi, and theta goes from 0 to pi. Theta goes from here to here, and phi goes from here to here, and you will cover the whole space. So in this case, if I want to get the omega, the solid angle that's subtended by a cone like this, in 2D geometry, if you want to get, you have an arc length. What's the arc length? ds. This is d theta, and this is r. What's ds? So you just multiply r d theta. So what's d theta? The angle in 2D is the arc length divided by r. In three-dimensional space, if you want to get d omega, you divide area by what? By the square of the r, not by r, by the square of r, in order to get what? Unitless. So this is, what's the unit here? S in centimeter, r in centimeter. You get the delta theta. It does not have unit. The unit is degree, of course. So here, if the area is in centimeter square, you have to divide by what? R in centimeter square, so that you do not get any centimeter, and it will be in degree. So in this case, this is what? Delta A over what? R square. So what will be delta A? Sine theta d theta d phi multiplied by r square divided by r square cancel, and you will have sine theta d phi. And this is what? Delta omega. Yes? This is the solid angle subtended by a cone. If you integrate over the whole space, if you integrate over the whole space, so somebody can Just tell me what's the delta omega is equal to what? Sine what? Theta d theta what? D phi. Now I want to get omega of the whole space. So I should integrate sine theta d theta from theta goes from 0 to what? To pi. Yes? And I should integrate from 0 to 2 pi for what? For delta phi. So this integration will give me what? 2 pi. And this integration will be what? Cosine theta from 0 to pi multiplied by 2 pi. What's cosine theta at pi? So this gives me 2 pi, and then this will give me what? What's cosine pi? Is -1. But there is a there is a negative sign from the integration, because the integration of sine is negative cosine. So this will give me what? -1 minus cosine 0 is what? 1. So this will give me what? -2 multiplied by negative is what? Is +2 multiplied by 2 is what? So the angle of the free space of a sphere is what? It's 4 pi. So the angle of the free space is 4 pi. And this agree with what we said here. So if you have an angle, a conical angle of an area in spherical geometry, just the representation is just d omega is sine theta d theta d phi. And if you want to make sure that this is the correct representation of the delta omega, just integrate over the full space. And what happened is in spherical geometry, this theta, to cover the whole space, this theta goes from 0 here up to what? Up to what? 2 pi. And the projection goes from what? From 0 to 2 pi. So you will have, if you will have the major circle on a sphere on the horizontal direction like this, if you rotate around phi, this will give you the major what? The equatorial circle, the major circle in this direction. Yes? And if you go from 0 to pi, this will give you the top hemisphere. Yes? If you go from pi to 2 pi, this will give you what? The lower hemisphere. So we'll have a lower and upper hemisphere. This will form a sphere. And this is the result. So I will stop here and start the new chapter next time. Did you have any question? Nothing? Thank you.